Okay, so put your hand up if you've got something similar to it that looks like it's a good fit. All right, so who can tell me what type of function you've used? Yes.
I used a polynomial of order 4.
Okay, so we have a fourth order polynomial. Anyone use something different? James?
Third order?
Right. So it seems that, yes, Andrew? Right. Okay, so Andrew's come across something that, yes, these data are actually sinusoidal. Excel is not capable of doing a sinusoidal regression, which is why we use a third order polynomial to approximate it. You'll learn in first year university why that actually works, but it does, as you can see by the graph. So we can generally use higher order polynomials to get a fit for most curves. Just be careful, though, because oftentimes there's a lower order one that'll actually be better. For instance, the third order polynomials in this case didn't have much increase over the fourth order ones, yet they greatly simplify computation, especially if you're trying to do this in real time over real traffic data, right? So before you jump to the higher order polynomials, try to check the other possibilities first. Okay, are there any questions on that? Put your hand up if you're good to move on. Great. So now we're going to take a look at part 3. And this is a considerably more advanced section. But I think most of you guys are capable of handling this. So this is cross-correlation. Now be careful of the terminology here because it's different than correlation. Cross-correlation is part of what's called digital signal processing, which we won't do too much of, but we will do this particular aspect of it because a lot of you will find it helpful in doing your analysis. So to start with that, we'll take another look at causation. If two variables A and B are positively correlated, we may hypothesize that A causes B. And as we know, B may cause A. What type of relationship would that be? In terms of causal or common cause or... Pardon? Yeah, I heard it somewhere, reverse cause and effect. We can rule this out if we can show that a change in B occurs after a change in A. For instance, if an accident occurs on the 401 at 5:30 and at 6 there's a major traffic jam, it seems obvious to us that the traffic jam didn't cause the accident. But a scatter plot hides that time variable. A scatter plot just shows that around that time, the frequency of accidents and the frequency of that traffic jam, or of bad traffic caused by the jam, went up. So how do we compare two variables and time? That's a topic that we'll come back to in just a second. Before then, I should just point out one thing that you have to be aware of. This rules out reverse cause and effect. It doesn't rule out common cause or coincidence. So saying that A follows B, that A, the traffic jam, happens after B, and therefore the traffic jam happens because of the accident is wrong. And it's so wrong that we actually have a Latin phrase for it, post hoc ergo propter hoc, meaning after this, therefore because of this. And it's also often abbreviated to a post hoc fallacy. So fallacy, for those of you who don't know, means a logical error. So be careful of that. Just because we can show that one thing happens after another doesn't mean that it happens because of that. So going back to our question here, how do we compare these two variables but keeping time into the equation so it doesn't get hidden and our analysis doesn't give us something silly like the traffic jam causing the accident that happened half an hour before? We can compare two variable and time graphs qualitatively. So to do that, we'll take a look at our Excel file again. And this time, we want the DSP correlation one. Right, so that's in your shared folder. And pull that up. And head over to the third tab, the Demo tab. So if we take a look at this plot here, we have our 3 red, green, and blue variables. I'm going to go ahead and delete the XY green one just to make it clearer for you guys. You can delete it if you want. We see that we have 2 data sets, our X and our Y. Now, if we look at these, we can see that they both have a peak, right? So if we think about it in terms of that example I gave before, this red X values might be the frequency of accidents, and this blue Y might be the density, so how congested it is. And we can clearly see qualitatively that there's a peak in both of these, right? And it makes sense then that we can look at this and see the difference in time between these 2 peaks, therefore how long it takes for the accident to cause the traffic jam. Does that make sense to everyone? Now what we might want to do is quantitate that. Whoops. So how do we quantitate that? The way we can do that is seeing how similar 2 data sets are to one another. So if we want to figure out how similar this one and this is, keeping the time into effect, we can look at each individual datum. So if we calculate xy, xy means multiplying the x value by the y value, right, which you can all see here is b2, the x, times d2, which is y shift, which is what we're using. You'll see y in a second. And we see 0, 0, and 0. And if we go down to where it's interesting, we have here 1, 3, and we get our xy as 3. Now, what happens if we have a very large x value along with a very large y value? How large will xy be? Really large, right? So if we have peaks over peaks, that's going to greatly increase our xy. And if we have troughs over troughs, then that won't increase xy much. But if we multiply a peak by a trough, then the small value of that trough is going to bring down a lot of the amount that the peak could come up with that. I heard what's peak. Peak means large values. So this peak up here, this one here. OK? Does that make sense to everyone? Put your hand up if it makes sense, if you're ready to keep going. Great. And if we then take these xy's and sum them up, so we see here sigma xy means the sum of all of them, we get 10. This 10 is a quantitative measure of how good or how well these 2 data correlate to one another. Now take a look at this shift value. Change it from 0 to 1 and see what happens. So we notice that the red peak then moves, or sorry, the blue peak moves closer to the red peak. With the blue peak closer to the red peak, should there be more or less correlation? Put your hand up for more. Put your hand up for less. OK, so we have 1/7 of the class represented in that poll. Let's try again. Put your hand up if you think that when we move the peaks closer together, we should have more correlation. And who thinks we should have less correlation? Right. So we should have more correlation because these peaks, when we put them together, they correlate better, right? A closer peak together means that it's better correlation. It means that xy, the product of these 2, is going to be greater. And for those of you who left that green graph on, you can see that it increases greatly. And sum of xy becomes 16. 16 is greater than 10, which tells us it's greater correlation. Now change shift to 2. So this shifts the data once more, and now our 2 data sets are right on top of one another. OK? So being on top of one another, now they correlate really well, and they give us 19 in sigma xy. Is everyone getting that? Put your hand up if you're good to move on. OK, we only have 5 or 6 people here. Are you guys doing OK? All right, Robbie's good. I see the right things on your screens. Great. So what happens then if we go ahead and graph these, right? So with 0 shift, it was 10 correlation. With 1 shift, it was 16. And with 2, it was 19. If we graph this, we get what's called the cross correlation. And to take a look at that, we can head to the main tab. So the main tab currently has a fair bit of other data there. We can get rid of that. So select that and delete it. And now head back to demo, and we can copy X and Y over. So again, Control C to copy it, then head back to main, and now select cell B5 and hit Control V to paste. So we can see that we have a graph of our X and our Y, and if we scroll down a little bit, we have this graph of the correlation. And we can see that peak there that we found when they were right on top of one another. So we can see now that we have a way of showing how shifted data peaks are. And if they're shifted when they have this maximum correlation, it means that we have a peak in one, and that then creates or is related to a peak in another at a slightly different time. Is everyone following that logic? Put your hand up if you get it. Okay, so it seems that people seem to be following fairly well. This gets a lot more interesting when we use actual data. So I'll start with these data in columns D and E of your More Data tab. So at the bottom, head to the More Data tab and select columns D and E, except for you don't need the header. And then we'll go Control C to copy it and paste that in to cell B5 as well. So now we get these two graphs. These are also identical peaks, but they look a little bit more interesting. And if we head down to the graph of correlation, we'll notice that it's cut off. So select this blue line, and we'll scroll down to find the bottom of this, and we'll notice that it's not actually graphing all of the data. So just click on this bottom right corner and drag it down. And you can go below if you want. It'll just have some zeros at the end. And now we can see that we have this peak here. So this peak here will tell us how delayed the data are. So does everyone follow so far? How are we on that last row? Yes. So select the blue line in the bottom graph. There you go. And then you see that blue box there, right? So scroll down to the bottom right and drag that down to get all of your data. Now this peak in the correlation is colored yellow. So if you scroll down, you should see a yellow peak here, or a yellow value here that is the peak. Has everyone found that?
Yes.
Okay, I'm hearing some no's. Who hasn't found it? So let's make sure that you have the data copied in. Okay, you're going to want to close that and reload. Yeah, because some of the calculation cells have been deleted. So for those of you who have found this yellow peak, we notice this 32 beside it. This 32 means that it's offset by 32. So we can head up here, and we see this data set has the peak here at about 40, and this one has it here at about 70. So that makes sense. That tells us that this second one is offset by 32. Now that seems all well and good, but not very useful. We can just look at it and see that that's how much the peaks differ. The reason this becomes useful is because in reality, data tend not to have this really nice curved structure like that. data tend to have random noise. So we're going to go back to the More Data tab and select the peak random data. So these are the same peaks, except with some random noise added. And again, we'll copy and paste that in. So you can see now that the graphs look qualitatively similar, except that we have a lot of random noise that's been added. Now, is it so easy to take a look at these and figure out the shift between them? Not nearly so easy, is it? Yeah, so the noise adds all of these little peaks here, and also little peaks on top of the big peak. Which one do we know is the true peak of the data? That's very difficult to tell. But with the math that this cross-correlation is doing, we can figure it out. So we can scroll down again and find that yellow peak value and find that it corresponds to an offset of 33. So adding this random data, it shifted it by 1 because random data does change it slightly. But we see now that the math here has correctly identified the offset. OK. Put your hand up if you found that, if you found the peak here as 33. OK, I'm only noticing 3 or 4. How about you guys on the end? Solomon, Alex, have you got it? Robbie's way ahead of everyone. He's doing his own thing. Oh, no, you're not. OK. All right, so are we good to move on? Let's do something that's actually applicable. I think you guys might find that more interesting to look at. So if you head to the More Data tab and this EW column in A and B, this is comparing eastbound and westbound traffic in one, or delay in one of Toronto's major highways on, I believe, the afternoon rush hour time. Or sorry, not afternoon, it was late at night. Late at night 2 Tuesdays ago. So we can select this and paste that in. So again, copy that and paste it in. So the first thing I'll draw your attention to is these two charts of the data itself. This data is at around 11 at night, so there should be no major congestion. Yet there is. And this is in the westbound direction. And this peak here, does anyone have any idea why that might have happened? OK, I know you know. Anyone else? How about you, Bill? Do you have any idea? No? So a peak that occurs in the delay when there normally isn't one is usually because of an accident, right? And in this case, there actually was an accident then. But look what happens here. There's a peak in the data, or in the delay going in the other direction. So this sort of ties into what the accident group and the comparing the same road in different directions group is looking at. This occurs because of this. When there's an accident, and studies have shown this, drivers going in the other direction tend to slow down to look at whatever is happening. And that causes a slight resultant peak there. What our analysis of cross-correlation can tell us is what the time delay is between the delay in traffic that the accident caused and the delay in traffic in the other direction. So we can scroll down, find this yellow value, and we find that it's 0. So what does that mean? So 0 means that there is 0 offset. So it means that the difference in the times that these two peaks occurred is 0. And that, of course, tells us that the traffic effect in one direction versus the other due to an accident is about the same, or occurs at the same time. If we got, say, a value of 6, what would 6 tell us, given that there's 5 minutes between each of these data points? Yeah, it would tell us a 30-minute delay. And there are cases for the groups that will be doing this type of analysis for which we find 30-minute delays. So that's an example of what we can do with this cross-correlation to figure out what the time delay is between peaks in the data where one variable is hypothesized to cause another. Is everyone on board so far? Has everyone found this maximum value there at 0? Not at 0. Are you using the same data set?
It is at 1 and 3. Yeah, me too.
At 1 and...
That's because you got that access.
Yes, you're right. So if I get rid of that, we now find 2 peaks at 1 and 3. You're right. Sorry about that. My bad. So a bit of a delay added there. The 2 peaks are at 1 is 5 minutes, 3 is 15 minutes, so around 5 to 15 minutes delay. All right? Does anyone have any questions as to how we got this, what it means, how we might go further on that? Okay, so I'll mention one last thing to you before we break off into our groups again and continue on with the activity. And that last thing is a technique known as autocorrelation. So if we correlate data with itself, peaks tend to amplify. And if it's periodic, these amplifications will be too. So to give you a better idea what that means, we'll show you. Head over to More Data and select Sine. And it's just one column, so select the one column and paste it over into both columns of our main page. And again, we should go down and delete the remaining data from the previous data set. So we now see 2 sine waves as expected here. For those of you who don't know what sine waves are, they're waves mainly. And the correlation is also very periodic. Does anyone have any idea why that might happen? No? Any thoughts, conjectures? So the reason that happens is when we have these two right on top of one another, since it's the same data, they should have the maximum correlation, right? And that makes sense, and we see this peak here. But then, if we move it across so that instead of this peak being with itself, this peak goes with this second peak, then we also have a high degree of correlation because one peak goes along with one that shifted alongside of it. And so that's why we have this secondary peak in the correlation here. So if we see this periodic vibration in the correlation data when we correlate data with itself, that implies that there's actually a periodic nature of that data with respect to time. And to give you an example of why that's useful, copy the sine random data, so that's sine except with some random noise added, and paste that in. Now take a look at this. Looking at that, can anyone see that it's periodic? Is there a periodic nature that's apparent by the graph? When you first look at it, there really isn't, right? There's too much random noise there to tell. Since we know what the graph originally looked like, we can kind of trace it back out ourselves and see that periodic nature, but it's difficult to tell from the human eye. But look what happens when we correlate it, right? It becomes a lot more apparent. So that's another example of how this can be very helpful if you, say, think that there's a periodic flux in traffic density over time, for instance. So we see this peak in the morning and this peak in the afternoon. If you do that over multiple days, you'll get a graph similar to this. And also, I was mentioning that bandwidth data before, how we had the going up and down with weeks and weekends. And again, if we autocorrelated it, we'd get a graph similar to this. So autocorrelation is a very good way of determining if a data set that varies with respect to time has any periodic nature. All right, so can you guys put your hands up if you're good on that, if you understand it, if you think you can use it? Not like if you can use it for your own project, but if you think you have the theoretical understanding to use it. All right, I'm noticing only Hannah over here has her hand up. All right. Are you guys doing okay, Alex? Solomon, are you paying attention? No, you're not. Okay, his loss. So that's it for the theoretical aspect of this. And now we're going to use the rest of the afternoon to work on our final presentation. So you guys already started in the morning. Now you have a bunch more tools you can use in order to help analyze two-variable statistics. And so we'll continue on working on the projects that you were this morning. And again, a couple things that you can think about for the final presentation. We'll get a lot more into this tomorrow. But how can these results be used to suggest a change to improve congestion? And myself and Agop and the counselors will all be going around helping you think of ways to do this. And how can this be done dynamically in an intelligent transportation system? So if you guys want to make a prototype, I know a lot of you were interested in doing some programming. We can also get you on the right track to do that. Just bear in mind, don't put anything on the website today. You'll see why that is tomorrow. So keep it on your W drive, and you can put it up on your websites tomorrow. All right, are there any questions about the presentation or about the data analysis techniques we just covered? No questions? All right, so we may as well get started working on the presentation. So I think you're all in your groups now, so should all be good to start. Yes?